Dear friends, welcome to the lecture of Riemann integral. In this lecture, we shall study a theorem on existence of Riemann integral. In our last lecture, we have defined Riemann integral functions, and in this lecture, we shall see what is the condition for Riemann integrable function in terms of upper sum and lower sum. There is also another condition for existence of Riemann integral, that is in terms of continuity of the function. But this is the theorem related to Riemann integrable function in terms of the upper sum and lower sum. The statement of the theorem is, let f be a bounded function on closed bounded interval a comma b. That is our consideration. F is bounded function and taken on closed bounded interval of real number. Then f belongs to this class Riemann integrable functions. We have denoted this in our last lecture. R a comma b means Riemann integrable function on the interval a to b. So f is Riemann integrable on the closed bounded interval a b, and this is if and only if f is Riemann integrable over the interval a to b if and only if for each epsilon greater than 0 there exists a subdivision sigma of a to b interval such that upper sum of f on sigma is less than, strictly less than, lower sum of f on sigma plus epsilon. So that means function is said to be Riemann integrable if upper sum and lower sum converge to each other. We earlier know that the upper sum is always greater than or equal to the lower sum, but here the theorem says that if you add a small quantity on the lower sum, then upper sum becomes less than the lower sum. So when we take the refinement of subdivision sigma, if this is subdivision and we consider the interval a to b, and if the intervals are divided into infinitely number of components, then the upper sum decreases and the lower sum increases, and they will converge to each other, and that means there is very small difference, or actually for Riemann integral functions they are equal when the component intervals are infinite. So thus here we have to prove the upper sum is less than lower sum plus a very small quantity epsilon. Now the condition is if and only if. So there will be two parts for this condition. First we shall assume that this holds, the upper sum of f on sigma is less than lower sum of f plus epsilon, that we shall assume, and then we will prove f is Riemann integrable. So we consider the proof as, first suppose for given epsilon greater than 0 there exists a subdivision, there is a subdivision sigma of the closed bounded interval a b such that this condition holds. We are assuming the second part first, and we will prove the first, that is f is Riemann integrable. Upper sum of f on sigma is less than lower sum of f on sigma plus epsilon, and we shall suppose this as first result. Now we will use the definitions of upper integral and lower integral. We have by definition, this is the upper integral of f, which is denoted by this symbol. This we have studied in our last lecture. Upper integral of f is equal to GLB of upper sum, and the lower integral of f, that we denote like this, is equal to LUB, least upper bound of lower sum on sigma. See that upper integral is the smallest value of upper sum. Greatest lower bound is actually the smallest value of that set, in that set, and here the lower integral is least upper bound. It is upper bound means maximum value of the lower sum, and therefore thus if you consider this upper integral, then upper integral, and if you consider any upper sum, then this will be greater than or equal to upper sum. See, if you consider the upper sum, So that is the smallest value. So this will be any value, and this is the smallest value. So therefore this will be greater than or equal to, upper sum will be greater than or equal to the upper sum of f on sigma. Upper integral is see, this is the smallest value. So therefore this must be less than or equal to any upper sum. This is smallest value, and therefore this is less than or equal to upper sum of f on sigma. And now what about the lower sum? The lower sum, that is lower integral of f is, so this is the maximum value. Least upper bound means maximum value. So this is maximum value, and therefore this will be greater than or equal to any lower sum f on sigma. See what we have considered is, now if we take an example of a set A which has the elements as 1, 3, 5, 7, 9, etc. For example, what is the greatest lower bound of this A? GLB for A is 1, so that is the smallest value. And what is the least upper bound of A? That is 9. So this means here this is the GLB, the upper integral is GLB of upper sum. In that case we consider the smallest value, and for the lower integral we consider, see this is lower integral, we consider the least upper bound of the lower sum. If it is the lower sum, then we consider its maximum value, and thus this integral, this is the smallest value. So here what we are writing, 1 is less than or equal to any x belongs to A. So that is the first value is the greatest lower bound. And what we are writing here is this is last maximum value, 9 is greater than or equal to any value x belongs to A. So this is the meaning of these inequality. The upper integral is less than or equal to any upper sum, and the lower integral is greater than or equal to any lower sum. And thus what we shall do is, we use these expressions here in the first inequality. So this is the upper sum, and this upper sum we now replace by the upper integral which is smaller than this. That means we are decreasing again this quantity, and that means so using these in 1, we get, see what we will do is, this upper sum we will replace by the upper integral, and this because we are decreasing this, and then the relation remains again. And what we are doing for lower sum, we are replacing lower sum by greater value. So this we are increasing, this we are decreasing, and therefore the inequality remains the same. So this is less than, strictly less than, lower sum is replaced by the lower integral of f plus epsilon. So you note this, that this we have replaced by a smaller quantity. So this side we have decreased and this side we have increased, and again the relation remains the same, less than. And here, but what is epsilon? Epsilon is any value, given epsilon or each epsilon greater than 0. So this is arbitrary, and this can be made as small as we want. So when epsilon is very small, this upper integral will be less than or equal to lower integral. So but epsilon was arbitrary, that we have considered, or arbitrarily small, and therefore we have therefore we get the integral, this is upper integral of f is less than or equal to lower integral of f. So this is the relation here we have obtained. Whenever this is the case, the upper integral becomes less than or equal to this lower integral. And but what is the usual relation? The usual relation we have is lower integral is less than or equal to upper integral, that is by definition. But by definition of lower and upper integral, this we have seen in our last lecture. Lower and upper integrals, the lower integral is the lower integral is less than or equal to the upper integral. And now see, these are less than or equal to each other. Here upper integral is less than or equal to lower integral, here lower integral is less than or equal to upper integral. This follows by the definition. This is always true, and this is true in this case, and therefore these together will imply they must be equal. If a quantity is less, two quantities are less than or equal to each other, then two must be equal. So these together imply the lower integral is equal to the upper integral, and this shows that the function f is Riemann integrable. Hence, or thus, f is Riemann integrable over the closed bounded interval AB. So this is the notation for Riemann integrable function. So this proves the first part. Assuming this inequality, upper sum is less than lower sum plus epsilon, we have proved f is Riemann integrable. That means its lower integral is equal to upper integral. Now we shall consider the other part. That means we shall assume f is Riemann integrable. Suppose, second part in the proof, because the conditions are if and only if. So if part and only if part. Now suppose f is Riemann integrable. Then what we will have, the upper integral is equal to lower integral. We will also write the definitions. Then the upper integral of f is equal to GLB of upper sum, greatest lower bound of upper sum, and this is equal to I will write LUB of upper LUB on any other subdivision of lower sum of f on tau, another subdivision, and this is equal to the lower integral. See what we have written. Because the function is Riemann integrable, its upper integral is equal to lower integral. But what is upper integral? Upper integral by definition is greatest lower bound of upper sum. And what is the lower integral? Lower integral is the LUB of least upper bound of lower sum. So thus all are equal. If the function is Riemann integrable, upper integral is equal to lower integral, and GLB of upper sum is equal to LUB of lower sum. And thus we now consider epsilon greater than 0, or we now consider the definition of greatest lower bound by the definition of greatest lower bound. So for there exists epsilon greater than 0 such that, now what is the relation for greatest lower bound? So this is the greatest lower bound we have, and here we will have any value we shall consider, upper sum of f on sigma, and that we shall consider that is the upper sum of f on sigma, that is the smallest value. Now if you increase it by a small quantity, that is epsilon by 2, epsilon or epsilon by 2, then that becomes greater than or equal to the upper integral, or strictly greater than, that becomes strictly greater than upper integral. So how we have written like this. Again we can consider the earlier example of the set A. So which set A we have considered? 1, 3, 5, 7, 9. Now what is the here the GLB? GLB is 1. GLB for A is 1, and if I increase this 1 by a small quantity, that is epsilon by 2, or we say epsilon by 2 can be considered as a 0.5, then this value becomes greater than one member, that is 1. So if it is increased by a small quantity, then this is that value will be greater than this one, and it does not remain the greatest lower bound. Or in place of this we can write 1 plus epsilon by 2 will be greater than 1. So that is what we have written. The upper sum, any upper sum is selected, any upper sum, and plus epsilon by 2 will be greater than or equal, strictly greater than the upper integral. So definition of GLB, there exists epsilon greater than 0 such that for a subdivision sigma, this happens for a subdivision sigma. Sigma of AB. So there exists, we can select a subdivision such that this member will be greater than or equal to this one, strictly greater than this one, because this is the smallest, and so therefore this value becomes greater, and that is, this can be simplified as, now we shall take this term on that side, that is upper integral, upper sum of f on sigma becomes greater than. So we will write the upper sum is greater than upper integral. See, this is to be written as. So upper sum of f. See here, what we have to consider is the smallest value. So this relation is to be corrected, that the GLB is this quantity, upper integral a to b. So therefore we should write this as the upper integral a to b is the smallest, and this is the smallest. So this becomes greater than upper sum, any upper sum on sigma plus epsilon by 2. So please note this. What is here is this is the or the relation we have considered as a is 1 3 etc. 1 3 5 7 9, and then what is the smallest value? This is 1 will be greater than upper sum can be selected as first 1. See, the upper sum can be this is the smallest value, and that will be greater than 1 minus epsilon by 2. We should consider minus epsilon by 2. So this is the smallest value, and that will be greater than a member of this minus epsilon by 2. So therefore this this will not remain the lower bound if we decrease it by minus epsilon by 2, and thus this relation gives the this quantity upper sum of f on sigma, that is upper sum of f on sigma minus epsilon by 2 is less than upper integral of f. Now we can suppose this as our second relation. Similarly, we use the definition of least upper bound. Similarly, by the definition of LUB, we get, see, this is the least upper bound is the lower integral. So lower integral, and this is the lower sum. So lower sum, and this is the maximum value. So if we increase this by some quantity, that is the lower sum of f on tau and plus epsilon by 2. So this is plus epsilon by 2, and that becomes greater than the lower integral. Of f. Lower sum plus a quantity epsilon by 2 will be greater than the lower integral a to b, and that can be verified by taking the example a as 1 3 5 7 9. Now what is the lower integral here? Lower integral is the LUB, means 9, and that you can consider the any sum, and then that can be considered as this is 9. So we can write this as 9 plus epsilon by 2 will be greater than 9. If you add this for this member, if you add epsilon by 2, that becomes greater than 9. So therefore a lower sum plus epsilon by 2 becomes greater than the lower integral, and we shall suppose this as our third relation, and now we can combine 2 and 3. So from 2 and 3 we will get, so here we have used the definitions of LUB and GLB, and now we are combining this from 2 and 3. We get, what is the second relation? we shall write this as the left side. Upper sum of f on sigma minus epsilon by 2 is less than the upper integral of f. And again the upper integral, here we can write this as equal to, see, upper integral is equal to the lower integral of f. Because of this, upper integral is equal to the lower integral, and that lower integral, this quantity is greater than that lower integral. So therefore this or that can be reversed, or that is the lower integral of f is less than the lower sum of f on tau plus epsilon by 2, and this may be taken as 3. See, it is one and the same. So we have reversed. Now why? Because we can write in continuation. So this is less than lower sum of f on tau plus epsilon by 2. And the middle quantities are equal. This upper integral and this lower integral are equal, and therefore we get this left side expression is strictly less than the right side expression, and thus that is the upper sum of f on sigma minus epsilon by 2 is less than lower sum of f on tau plus epsilon by 2. Now we can transfer this minus epsilon by 2 on right side of this inequality, then it becomes plus epsilon by 2, and therefore this is upper sum of f on sigma is strictly less than lower sum of f on tau plus epsilon by 2 plus epsilon by 2, that is epsilon. So thus we have obtained this relation. Now what we require is the upper sum of f on sigma is less than lower sum of f on sigma plus epsilon, and here we have considered the subdivision sigma and tau. For second relation we have considered the subdivision tau, but we can consider a refinement of both these as sigma union tau. Now sigma union tau is a refinement. It is a refinement of both sigma and tau. Therefore we can replace both sigma and tau by sigma union tau, because in the refinement the upper sum decreases, so that side decreases, and in the refinement the lower sum increases, so it remains, the inequality remains the same. So therefore we get, so what we will have is upper sum of f on sigma union tau is strictly less than lower sum of f on sigma union tau plus epsilon. So this is the relation that we have obtained taking refinement. Why we have done this? Because here the subdivision may be different, or actually different. Sigma, here subdivision is considered as sigma, and here we have considered subdivision as tau. It is not necessary that the subdivision must be the same, but we can make it same by taking refinement of both these. So increase the number of component intervals, that is the refinement, and we can take the refinement as union of both these subdivisions, and then we can replace each subdivision by this refinement, and now the result is of this type. Upper sum of f on sigma is strictly less than lower sum of f on sigma plus epsilon. In place of sigma, here is sigma union tau, that is a subdivision. So this is a subdivision, and or otherwise we can rename this as epsilon sigma itself. So we can rename this to get exact result, this one. So now renaming, it is a type of subdivision. Renaming sigma union tau by sigma, we get the result, that is upper sum of f on sigma is strictly less than lower sum of f on sigma plus epsilon, and this is the required result, and this proves the theorem. So this completes the proof. So thus we have proved the theorem on existence of Riemann integral in terms of relation between upper sum and lower sum. They are converging to each other, that means they are nearly equal. or almost equal in the number of intervals are infinite. So then the function becomes Riemann integrable. So this is about the theorem. The remaining part we will continue in our next lecture. Thank you.